Welcome to episode 11 of the Physiology 225 podcast. I'm your host, Dr. Jim Davis, and today we're focusing on one of the most fascinating and essential processes in the nervous system, action potentials. These electrical signals are the foundation of neuronal communication, enabling everything from reflexes to complex thought. So let's break it down step by step. To start off, we need to understand what is an action potential. Simply put, an action potential is a rapid, temporary change in a neuron's membrane potential that ultimately allows the cell to send a signal. Unlike graded potentials, which we talked about in our previous episode, action potentials are all or nothing events that occur once the membrane potential reaches a specific voltage, also known as threshold. Action potentials happen in three main phases: depolarization, repolarization, and hyperpolarization. But before we talk about each of those phases, let's do a quick review of resting potential. Remember, before an action potential begins, that's where a membrane's at, or a neuron's at, resting potential. This is typically around negative 70 millivolts. This steady state voltage is maintained by the sodium-potassium ATPase pump, which actively transports 3 sodium ions out and 2 potassium ions in. This ultimately keeps the inside of the cell more negative, and this pump requires ATP, which emphasizes its energy-intensive role. Next, we have leak channels. These leak channels allow for a small amount of potassium to exit the cell while allowing an even smaller amount of sodium to enter the cell. This contributes to the negative resting potential because potassium movement out of the cell is favored. Finally, there are negatively charged proteins. These large proteins that are near the membrane are unable to cross, and therefore the cell's interior becomes more negative. At rest, voltage-gated sodium and potassium channels are closed. Importantly, the voltage-gated sodium channels have 2 gates. There's an activation gate, which is closed at rest, and an inactivation gate, which is opened at rest. However, both gates must be open for sodium ions to flow through that, and this will be critical when the membrane potential changes during depolarization. So this leads us to depolarization. So when a stimulus causes the membrane potential, or the graded potential, or the sum of graded potentials causes membrane potential to reach threshold, which is typically around negative 55 millivolts, an action potential is initiated. So here's what happens. The voltage-gated sodium activation gate opens. These activation gates allow for sodium ions to rush into the cell, and this influx of sodium ions is driven by the strong electrochemical gradient. There's more sodium outside of the cell than inside, not to mention the inside of the cell is negative, and so there are 2 forces causing sodium ions to go in. The voltage-gated potassium channels open slowly, which only allows for a small amount of potassium efflux during depolarization. This rapid influx of sodium depolarizes the membrane and increases membrane potential from negative 55 millivolts to approximately plus 30 millivolts. When depolarization reaches its peak, the sodium inactivation gates begin to close, which prevents further sodium entry into the cell. This rapid depolarization is crucial for propagating the signal along the neuron. It's essentially the go phase of the action potential. Now, once those sodium inactivation gates close, while the sodium inactivation gates are closing, those voltage-gated potassium channels are finally fully open. And this allows potassium ions to flow out of the cell completely, and it's driven by their concentration gradient, making the cell inside more negative. This phase brings the membrane potential back towards its resting state, restoring the cell's readiness for future signals. However, the membrane potential briefly becomes more negative than the resting potential. When this happens, we've reached the hyperpolarization phase. And the hyperpolarization phase goes from about negative 70 to negative 85 millivolts. During this time, potassium efflux continues because those voltage-gated potassium channels close so slowly. As a result, extra potassium leaves the cell. And the other thing that occurs during hyperpolarization is that the sodium-potassium pump and the potassium leak channels restore this resting potential to negative 70. Additionally, the sodium inactivation gate reopens while the sodium activation gate closes. Ultimately, we're resetting these channels for the next action potential. Hyperpolarization ensures the neuron temporarily resists another action potential, a phase known as the refractory period, which helps regulate signal timing, which we'll talk about in a future episode. I want to go back really quickly to the threshold. Why is this so important? The threshold is a critical voltage that must be reached to trigger an action potential. It's like a trigger point. Once the membrane potential hits this level, the action potential becomes self-sustaining and ensures reliable signal transmission. As mentioned previously, this is an all or none phenomenon. Either we have an action potential or we don't. We don't have half of one and we don't stop in the middle. And so just to be clear, I want to point out some key differences between action potentials and graded potentials. Action potentials occur along the axon, while graded potentials generally occur in the dendrites and cell body of a neuron. Action potentials, as just mentioned previously, are all or nothing, whereas graded potentials vary in strength based on the stimulus. And then finally, action potentials involve voltage-gated channels, while graded potentials rely on ligand-gated or mechanically gated channels. So let's summarize this episode with our key takeaways. Action potentials are rapid, all-or-nothing electrical signals that allow neurons to communicate effectively. They involve three main phases: depolarization, repolarization, and hyperpolarization, with distinct roles for sodium and potassium. Sodium channel activation and inactivation gates coordinate to control sodium flow during each phase. Voltage-gated potassium channels begin to open slowly at threshold, but ultimately play a crucial role in repolarization. The threshold voltage is essential for initiating an action potential and ensures it propagates reliably. So that's it for episode 11. I hope this expanded overview of action potentials has clarified how neurons send signals. Join me next time for episode 12, where we'll explore action potential conduction and how these signals travel along neurons. Until then, keep questioning, keep exploring, and stay curious.